So hello, and thank you so much for having me. It's been an honor and a joy to celebrate this week. So I'm Diana Powell. I'm an assistant professor at the University of Chicago, and today I'm really excited to talk with you all about connecting planet formation and planet characterization. And I hope to demonstrate to you all why we're closer than ever before to understanding the formation and evolution of planets. And this is in part due to insights gleaned from microphysics. And so in this talk, when I say microphysics, I mean small-scale processes like the evolution of dust or particles in the presence of gas. And so the key question behind all of the research I'll talk about today is what is the origin, evolution, and nature of planets? And to address this question, we need to characterize planets and the planetary material in protoplanetary disks. And in particular, I want to demonstrate how we can use theoretical microphysical tools to uncover fundamental properties of both disks and atmospheres. But first, let's take a step back and look at the picture of planet formation and evolution that has emerged. So planet formation begins in protoplanetary disks. So these form as the host star forms. And planets form either from the accretion of solids and gas or from the direct gravitational collapse of material. So these protoplanetary disks constitute the building blocks of planetary systems. And all theories of planet formation require accurate disk conditions to predict accurate planetary properties. Then, once the bulk of the disk dissipates, a young planetary system remains. And then, as time progresses, the planetary system will evolve. And we're all very lucky to be alive at a time where we can observe each of these stages of planet evolution directly, and in unprecedented detail. So we can now observe protoplanetary disks directly, such as the disks observed in high resolution shown here. And as a bonus, we can actually observe active planet formation occurring in disks. So we can see this in systems like the PDS-70 system shown here, where you can see 2 points with the arrows that are thought to be giant planets undergoing accretion. We can also observe young planetary systems directly, like the Beta-Pic system shown in the bottom left, where you can see a debris disk and 2 planets. And finally, we now have observations of over 4,000 evolved exoplanets and detailed constraints from solar system planetary science and cosmochemistry. So this is all fantastic, and really in my lifetime. But despite this phenomenal and ever-increasing array of observational data, we're still looking at snapshots of planetary history. And so what I really want to know is how can we relate these disparate evolutionary stages to learn about the formation, evolution, and nature of the full complement of planetary systems. And so the way that I approach this understanding planet formation and evolution is from the perspective of characterizing both protoplanetary disks and exoplanet atmospheres to uncover their detailed chemical composition and physical properties. And I mostly do this using microphysics. So I'll get back to discussing microphysics in more detail in just a moment. But before I do that, let's talk about what it'll really take to make this connection. So what are we actually looking at when we observe protoplanetary disks? So observations of protoplanetary disks are primarily observations of small dust grains and some different trace gas species, such as carbon monoxide. And these recent observations can be spectacularly angularly resolved. So we can see protoplanetary disks in this brand new detail. So here I'm showing the D-Sharp ALMA survey of disks at 1.3 millimeters, where you can see the stunningly high resolution. You can pick out different morphologies, all the way from smooth axisymmetric systems to, maybe you can't see it here, but even large-scale spiral arms. But despite this level of detail, there are rarely direct probes of some of the main disk properties. So we're still uncertain about things such as the total mass in these systems, and then the detailed compositional properties of the solid and gaseous mass constituents. And this is all particularly true in the planet-forming regions of the disk. And these properties all change with time, such that evolutionary disk models are essential to understand disks and planet formation. And so to get more of an idea of why determining the composition of protoplanetary disks is difficult, let's take a look at this vertical cross-section here. So the system's host star is on your right, and then the disk flares out at larger radii on your left. Planets form in the disk midplane, so this is a region of particular interest. However, in the midplane, the disk composition and mass distribution is changing with time. So your solid particles will move inwards in the disk, If they're coated in ice, they'll eventually reach hot regions of the disk, where they'll lose their volatile icy component back to the gas phase. All of this is changing the mass distribution and composition. You also have mixing going on to smooth different gradients, but this happens as a function of time and changes composition. And you often have gas in the upper regions of the disk that's optically thick, such that you're seeing emission from the upper disk regions and not the midplane directly. And this all happens to be particularly true in the inner regions of protoplanetary disks, where we know that planet formation is common. OK, so I hope that I convinced you that disks are these non-equilibrium objects that are difficult to model, as well as difficult to observe. But what about planets? And so we've heard more about planets this week. But when we're thinking about detailed properties, what are we actually looking at? And so a primary source of the detailed information about planets that I'm so interested in comes from the atmospheric observations. And so I'm going to show you an example of some of the data for these observations here for young planetary systems in emission on your left, and for evolved planets in transmission on your right. And so I think I'm showing 10 Jupiter-mass planets, young ones in emission, and 10 in transmission. And to show how these fields are rapidly evolving, these are all spectra before JWST, and here's what the corresponding spectra look like now, here for individual objects. And so we're now looking at a much longer wavelength coverage and much higher resolution. But despite this level of detail in these objects' atmospheres, these observations are both shaped by, and their interpretation is complicated by, non-equilibrium atmospheric processes, such as the formation of clouds and hazes and ongoing photochemistry. And so to get more of an idea of why determining composition and properties of planets is difficult, let's take a look at this planetary cross-section. So here you have a planetary interior or surface, depending on the type of planet you're looking at, and then the atmosphere. However, almost all planets with an appreciable atmosphere tend to be covered with clouds. And clouds can completely obscure signatures of atmospheric composition. They can also alter the observed gas phase abundances, even if you don't see the clouds. And they set the atmospheric chemistry. And in addition to the complicating presence of clouds, the majority of planets orbit host stars, which are highly radiative, so they can really blast these planets with high-energy light that can activate photochemistry. And then photochemistry can then cause the formation of hazes, a different type of aerosol that can act similarly to clouds and obscure what we're looking at. And of course, all of this interacts with radiation in the atmosphere and mixing. So all of these processes feed back into each other. And while this may seem detailed, these are all effects of first-order importance when looking at a spectra. So we can see all of these very, well, they're all first order in shaping what we see and how we interpret it. We hope we can see them clearly. And so in both cases, many of the complications with determining chemical compositions and fundamental properties boils down to a need for better understanding of microphysical processes. And so many of the key common processes are shown here. And I'll explain these processes in a bit more depth throughout the talk. And hopefully by the end of this talk, you see how microphysics applies in several different contexts and is crucial for understanding these systems. And so to make the connection between protoplanetary disks and planetary atmospheres, we need better physical models to interpret current and upcoming observations. And I'll argue in this talk that microphysics will be important and may well be key to understanding the origin, evolution, and nature of planets. And so I'll start by talking about some initial work with microphysics that we've done to tie planet formation to planetary characterization. I'll start by talking about planetary atmospheres with a focus on clouds and photochemistry, and then I'll move on to talking about protoplanetary disks and their fundamental properties, such as the total mass and their composition. So let's talk about clouds. So everyone here has some intuition about clouds from our familiarity with clouds on Earth. But clouds are important beyond Earth and are in fact the dominant opacity source in most planetary atmospheres. Clouds are important tracers of atmospheric physics, such as mixing and chemistry. Clouds set the planetary climate through regulating radiative transfer and chemistry. And clouds must be understood when determining atmospheric abundances. Also, often the clouds are the only thing that we can see in an atmosphere. So it's an absolute necessity that we understand clouds when we're interpreting planetary atmospheres. And it's now more clear than ever before that clouds are abundant in exoplanet atmospheres, where they have a first-order impact on atmospheric spectra and planetary climate. So here I'm showing that we now have 4 and counting exoplanets where we can directly see what the clouds are made of. So since the very first observation of an exoplanet atmosphere, HD 209, we've known that clouds are important in shaping atmospheric spectra. But now for this planet, we even know what the clouds are made of. So in this case, some mixed silicates. And I'll talk a lot about clouds in this talk. If you're not used to clouds on exoplanets at all, a lot of them are rocks here on Earth, but clouds in other places. And these observations of clouds have the potential to tell us so many things about the fundamental properties of exoplanets. So from their climate, to the atmospheric properties, to the atmospheric composition. And given this, it makes sense to understand how clouds form and evolve from first principles. So on the right here, I'm showing an example of some of my calculations of cloud properties in planetary atmospheres. So I'm plotting the mass density of different cloud species, so each color is a different cloud species, as a function of their particle radius and pressure in the atmosphere. And all the properties of clouds that we're seeing here on the right are calculated using the microphysical processes on the left. And we can use this framework to predict how clouds will look at different locations on the same planet. So here I'm again showing cloud mass densities, but now as a function of atmospheric longitude, well, planetary longitude, and pressure. And here I'm focusing on the case of a hot Jupiter. So we've heard about hot Jupiters. They're Jupiter-sized planets that are relatively hot. But they're also this really exciting cloud laboratory. Because they have such extreme insolation gradients, we expect different clouds to form at different locations on the same planet with the same background bulk atmospheric properties. And so we can get a sense of how clouds vary across this planet. So we can zoom in on different regions. So now I'm plotting number density as a function of particle radius and pressure on the east limb, where clouds grow to relatively small sizes. They exist in the upper atmosphere, and we don't see so many cloud species forming. Versus the west limb, where clouds grow to much larger sizes. They grow deeper in the atmosphere and should have a very different impact on the spectra. OK, so we know that clouds are different at different locations. But now, for the first time, we have reason to believe that our predictions are accurate because we can observe planet spectra at different locations on the same planet. So here I'm showing the first limb-resolved transmission spectra of an exoplanet taken with JWST. So here, this is the famous exoplanet WASP-39. And what we're looking at here in the two different colors are two spectra taken of the same planet but at different locations. And as we predicted with our cloud models, here we see damp spectra on the cooler west limb, which is likely due to enhanced cloud formation in this region, as well as to more transmission features on the east limb, so indicative of a more clear atmosphere. And the cloud models that I presented here are essential for both interpreting observations of individual objects, as we've just seen, but also for understanding trends across populations of planetary atmospheres. So here I'm showing an example of two observational trends that my collaborators and I have been able to reproduce and explain. So on the left is a trend in water amplitude as a function of equilibrium temperature for hot Jupiters. And on the right is a trend in dayside and nightside brightness temperatures, again for a population of hot Jupiters. And in both cases, you need microphysical clouds to understand these trends. And trends like this, so thinking of planets as populations and their detailed atmospheric properties as populations, are becoming increasingly numerous in the era of JWST. And so on that note, thus far, I focused my work on a class of exoplanets known as hot Jupiters, which have been the most amenable to detailed observations. But we're now beginning to observe terrestrial planets in more detail, which means that we need to be ready with adequate models. And I'll note that many models of terrestrial atmospheres have their heritage based on the study of Earth. And while we all want to find Earth twin, it's most likely that we'll uncover a great diversity of terrestrial planets that will all be incredibly interesting in their own right. And particularly this will be true as we observe planets that orbit stars that are quite unlike our own. And in recent work, I've demonstrated that we can actually fool ourselves into believing a certain conclusion if we don't expand the range of potential atmospheres that we consider for terrestrials. So in particular, I've shown how a planet with a substantial atmosphere and a thick night-side cloud deck could mimic observations of a planet with no atmosphere at all. So we could be wrongly claiming that a planet hosts no atmosphere when it may host a substantial atmosphere. And so ultimately, we need better observations to distinguish these two cases and a broader range of models to consider the range of atmospheres that we might be encountering. So yeah, here I show a case where the observations of these two planets would look the same, one that has no atmosphere, one that has a very substantial atmosphere. Okay. And so we've gone through some of the exciting things that we can uncover through a study of clouds and exoplanet atmospheres. But now let's briefly turn our attention to the microphysical process of photochemistry and how this impacts atmospheric observations. And this will be very brief. So photochemistry is chemistry that's initiated by molecular interaction with UV light. We know that photochemistry is crucially important for all planetary atmospheres in our solar system, where it's integral to both habitability and climate. So here I'm showing the ozone formation and destruction cycle on Earth. And without ozone, which needs photochemistry, life here would be completely different. And so the question previously has been, do we also need a detailed understanding of photochemistry to understand exoplanet atmospheres? And we now know with JWST that the answer is a resounding yes. So photochemistry is important in shaping the climate and composition of exoplanet atmospheres. And we know this because we were able to unambiguously detect photochemistry in an exoplanet for the first time. So we have this unambiguous detection of a photochemical product. And the same photochemical product has already been detected in a handful of other exoplanet atmospheres. And so this all indicates that photochemistry is likely to be important in shaping planetary climate on exoplanets as it is here in the solar system. Okay. So I've briefly discussed the importance of understanding clouds and photochemistry in substellar atmospheres, which is important in constraining planetary properties. But now let's turn our attention to protoplanetary disks, which are the birthplaces of planets. And I'll start by talking about the important question of how much total mass is in these systems. And so the question of how much mass is in protoplanetary disks is fundamental for planet formation and evolution. So the amount of total mass in the system affects the final composition and structure of the formed planets by affecting how the evolution of solids and gas happens in the disks as planets are forming. However, unfortunately, we cannot directly observe the main mass constituent of disks, which is H2 gas. So we instead have typically relied on some tracer to H2 ratio. And not only do we fundamentally not know what these ratios are, but we also have reason to believe that the most common tracers of mass, so dust and carbon monoxide gas, have abundance ratios that change significantly with time and radius in disk systems. So it's really hard to know a priori what this ratio is. So how can we measure the total disk mass without an assumed tracer to H2 ratio? We need an answer if we want any hope for planet formation models to be predictive. And so we can begin addressing this question by considering multi-wavelength observations of disks in the millimeter. So unlike planets, we can observe disks in the millimeter quite readily. And here I'm showing a visualization of observations put together by Dr. Sean Andrews of here one disk, TW Hydra, at different observing wavelengths. And you can see that the disk's radial size appears remarkably smaller at longer observing radiuses, or longer observing wavelengths. And so what we're seeing here, because at millimeter wavelengths we're basically looking at emission from a particle of a size comparable to the wavelength we're observing, we're looking at a sorting of sizes of dust grains in the disk. And using these observations, we're able to apply a knowledge of particle aerodynamics to determine how much gas must be present to force the particles to their current locations. And so in particular, we use knowledge that we think particles drift in disks. And so we think they drift, so move towards their host star, because the gas feels this outward pressure gradient that enforces a drag on the particles that removes some of their angular momentum and causes them to end spiral. And so we can use these observations of particle drift to trace the aerodynamic properties of the observed particles and then determine the total gas mass. And we can do this following the simple equation here on the right, where the properties I've circled here are all determined empirically. And I won't go into more details here, but we can use this method to derive the total disk mass without assuming a tracer to H2 ratio, because we only care about where the particles are located, which is dependent on their size, and not on how many particles there are. And we were able to apply this model to 7 protoplanetary disks with multi-wavelength observations in the millimeter that show decreasing disk radial extent with longer wavelength. So here I'm showing 3 out of the 7 disks in our sample. And we can do a lot with this modeling, but right now I'll focus on the key thing that we found, which is that disk masses are larger than we initially expected. So here on the left in black, I'm showing total gaseous surface densities derived from this method compared to previous tracer-derived surface densities, where we see that the disks in our sample are 9 to 27% of their host stellar masses, which is very massive. So that's orders of magnitude, an order to multiple orders of magnitude larger than we previously saw from other tracers. And so what that means is this work leads to a qualitatively different picture of disks, where they may be more massive than previously appreciated. So in particular, we're thinking about a dust mass as an order of magnitude larger than we previously thought. And these qualitative changes to models of protoplanetary disks have significant implications for theories of planet formation. So we're still working out what all those implications are, but the dominant formation process of different planets can change in this picture. And intriguingly, these new models of disks have also helped shed new light on the composition of the systems as well. And so in particular, there's this massive literature that suggests that carbon monoxide gas, which is one of the primary tracers of all the fundamental properties of disks, is missing or depleted in disk observations. And so to address this problem, I coupled my model for protoplanetary disks that we just saw with an adapted version of the models to study clouds and atmospheres. But in this context, I'm looking at the formation of ice on dust in disks. And what we found is that you can build a novel picture of CO ice formation and evolution in disks that solves this class of mysterious observations of missing CO gas. So in particular, you can funnel CO gas to regions of the disk we can't observe it well. So all the CO gas from the upper midplanes of the disk will be funneled to the midplane region, where ice is formed on large particles. These large particles undergo drift. They'll eventually reach hot regions of the disk, where they'll lose their ice component back to the gas phase. And then that enhanced gas in CO is then accreted onto the host star. And so with this modeling, we can find good agreement between our results and observations. So that's what I'm showing in the small plots here. But what we found that was kind of surprising is that these small-scale microphysical processes both regulate the observed abundances of CO gas and are crucial in determining the composition of these large-scale, very massive disks. And using this model, we're able to resolve inconsistencies in estimates of the disk mass using different tracers and constrain several key properties of disks that are essential for models of planet formation. Okay, so I've talked about understanding substellar atmospheres using cloud microphysics and photochemistry. And I've discussed uncovering fundamental properties of atmospheres using, of disks using particle aerodynamics and ice formation. And this has led us to several new breakthroughs with the help of microphysics. So we've seen that clouds drastically impact observations of atmospheres, and they can be used as a tool for testing our physical understanding. We've learned that photochemistry shapes exoplanet atmospheres, that disks may be significantly more massive than previously appreciated, and so planet formation might happen in different ways than we had thought. And ice microphysics shapes the compositional distribution of protoplanetary disks. But this work is really just beginning. So we still have so much to uncover about both disks and atmospheres, and what these two endpoints of planet evolution could tell us about how planets form, evolve, and ultimately what their fundamental natures are. And I think I have some extra time, which is great, because the best part of any talk are the questions. So I hope you have some.
Yes, questions?
One that was very interesting, by the way, but one thing I was missing, or a word I didn't hear, and since I'm a solar physicist, I would like to hear is the question of magnetic fields and what dynamical role they would play in these scenarios.
Great, so I'll answer that. Well, the place where I think the most about, I can answer it for both. So we think magnetic fields should really shape the atmospheric dynamics in different planets, both for giant planets and for small planets. Observationally, so if you have a lot of magnetic drag, you change the flow of an atmosphere from like something that could be a super rotating jet around the equator to something that's a bulk day to night side flow, and that really changes what we expect from observations and how we interpret planets. And also gives us a way to constrain the magnetic field, so a lot of nice things coupled there. So far, it looks like hot Jupiters, at least, don't have incredibly high amounts of atmospheric drag, such that we don't see large magnetic effects in their wind patterns. But that's just so far, so I think it's an interesting question to keep in mind. Also, the magnetic field should interact with photochemical products and photochemistry. So far, based on observations, it's a little intractable for atmospheres, but useful. Then for disks, we think the magnetic field sets a lot of how much mixing happens in disks, so how much turbulence. If you could think of a really great way to measure disk turbulence, which I tried to do a bit with the carbon monoxide, then that's kind of a $1 million question. So if we really understand what disk turbulence is doing, we know a lot about how disks evolve with time. But we think it's related to how much the magnetic field couples with the disk, depends on the star's magnetic field and the flux of cosmic rays, all of which are still relatively uncertain.
All right, Diana, I just want to make sure I got it. So I think you showed a study where a high cloud deck produces a very hot day-side temperature. Sorry. And so, of course, there's this enthusiasm to go and measure the day-side temperatures of a lot of rocky planets. Thank you. As a way of ruling out the presence of an atmosphere. So are you saying that just measuring the secondary eclipse alone is not sufficient and we have to measure phase curves? I just would like your, are you saying that that method is not a good idea? I'd just like to hear your thoughts about, because there's this plan to sort of put at least 500 JWST hours into that exact measurement. And so what is the implication of this for that idea?
Yeah, so I really outline a particular picture, but a plausible picture, where if you have this optically thick night side cloud deck, you do make the day side hotter, you funnel emission to the day side, we see the same effect in hot Jupiters, and you make the night side look colder. So unfortunately, phase curves don't help you. You still would get a very hot day side and a very cold night side. The big question, though, here is how common is this effect? And we think it's most relevant for the hotter terrestrials, and then any terrestrial that has a limited volatile inventory. So it could be relevant across a range of equilibrium temperatures. I think it's something we really should keep in mind for the hottest ones. But in terms of observing strategies, like with JWST, we're very limited. You have phase curves, you have day-side temperatures. I think what this study has shown me is that we're really not at a very constraining place yet with the observations. I think we can tell pretty resoundingly if there is an atmosphere. I think we need more detailed modeling to know the likelihood of whether there's not.
Great talk. Going back to the clouds, and you showed the JWST observation with the SIO. What do you think are the most important observations to determine the composition of those clouds?
Yeah, so definitely the longer wavelengths with MIRI. I'm now calling MIRIs the longer wavelength observing mode of JWST. And what it seems to be particularly good at looking at is photochemical products and cloud species. So it's kind of the non-equilibrium process observing mode. And so surprisingly, we found so far that you can get pretty distinguishing observations of what the clouds are made of with MIRI observations, which I thought would be difficult. It's like these large error bars, not very high resolution, but they're being quite distinguishing so far. So MIRI long wavelength observations.
Since we're on clouds now, I was asking you this earlier, but I'm curious, because this paper, the English paper, is not out yet. It's accepted?
Yes.
Okay, so we're all seeing this for the first time.
Yes.
So I get to ask a question about it. So WAS-17b, do you know anything about the host star? Is it metal rich, metal poor, or anything else that could help us understand what might drive that kind of silicate feature?
You did ask this question. I don't know off the top of my head, but my memory is that it's not too different from a solar type star. Okay, I should check myself. But
maybe solar metallicity type object. It's a big feature.
Yeah. Yeah, so they're already looking different from the brown dwarf objects. Yeah.
Okay, let's thank Diana again.